try and do the same thing for inductors that we've done for capacitors, and so we're going to continue the idea of inductance from capacitors over into inductors. And so we're going to see that when we apply an alternating current across an inductor, it's going to induce a voltage. And we already know that what inductors, the cause of inductors inducing a voltage is the change in current through them. And they induce a voltage when there's a change in current through them because the current through an inductor sets up a magnetic field inside that inductor. And so the voltage across the inductor is always induced to oppose that changing magnetic flux through the inductor, and by doing that it opposes the change in current through the inductor. We're going to find that the size of that voltage depends on the inductance of the inductor and the frequency of the supply. Inductance of the inductor, what does that do? How can we make an inductor have a bigger inductance? What kind of physical things can we change about it?
We can give it a core.
Yeah. What sort of core?
Iron core.
Nice. So, an iron core, or in fact a ferromagnetic, any ferromagnetic material as a core. If we have a ferromagnetic core, that acts to amplify the magnetic field that's created by the windings of current going around the solenoid. What's the other main thing, the other thing that we can change about the inductor to give it bigger inductance?
Is it density of coil?
Boom! Density of coils, like the number of coils per metre length of solenoid. Oh, we say density. And so those two factors, as we increase the inductance by increasing the density of the coils, by having either more coils or the same number of coils in a shorter length, or by putting an iron core into our inductor, those things increase the inductance, and by doing so they increase the voltage we see across it when we put an alternating current through it, and so they increase its reactance. The other thing that the reactance depends on is the angular frequency of the supply. What we know about inductors is they induce, the induced voltage on an inductor depends on the rate of change of magnetic flux, which depends on the rate of change of current through the inductor. If we have a higher frequency, AC, that means that the direction of our current and the size of our current is changing more rapidly, so we get a greater rate of change of current, and by doing that, a greater rate of change of magnetic flux. And that means that as we increase the frequency of the supply, we're also going to increase the reactance of the inductor. And so we put all that together to come up, like we did for the capacitor, with an equation for the reactance of an inductor. So we end up with these two equations. The one that pops up most commonly is the XL, is omega L. It's not that useful because very rarely do we have a number for the angular frequency of our circuit. So a much more useful equation is to pop in the omega is 2 pi f and just have the equation as XL is 2 pi f out. And hopefully you're seeing a real similarity with the reactance to the capacitor. The only difference is with the inductor, its inductance increases as its reactance increases as we increase the frequency, and it increases as we increase the inductance of the inductor. The capacitor was the opposite. Its reactance decreased as we increased the frequency, and its reactance decreased as we increased the capacitance.